Okay, I think we can go ahead and start this session. Uh, so my name's Jeff Carlin. I'm the deputy lead of the Rubin Community Science team. I will be chairing this session. You're also going to hear from a couple other members of the community science team. We're going to help you get started with early data preview 2. I think by now you probably all are aware that we have a code of conduct, but do reach out to either me, Federica, or Sandrine if you witness any violations of the code of conduct. Reminder, if you're on Zoom, please remain muted unless you unmute to ask a question. And a reminder in the room, if you have a question or comment, wait for a microphone to get to you so that the people on Zoom can actually hear. Okay, so our agenda, I'm going to give you a brief intro to the data set that makes up EDP2, and then you're going to get a brief demo of the portal, how to access data through the portal from Gloria Fonseca Alvarez, and then a notebook demo from Christina Williams. You're welcome to raise your hand at any point if you have any questions or issues, and we'll try and get those sorted. So as I mentioned, the Rubin Community Science team is a team that I'm part of, that all three of us are a part of. Our role is to support you as you try and do science. So many of us pictured on this slide are here this week. So if you have any questions at all, feel free to track one of us down. So this just mentions a few related sessions. Most of them have already passed, but I think I hear the Monday recordings are now available on the website, so you can go check those out, and the slides are available for each session. So there was an intro to Rubin, an overview of the early science program, including Data Preview 2, a data access with the Rubin Science Platform session. So those were all on Monday. And then tomorrow, you can hear updates from the Science Pipelines team on how things have changed in the pipelines over the past year. A reminder that the community forum is your sort of help desk, your place to reach out if you have any questions about the data products or you're having issues accessing things. We, the community science team, monitor the forum and will endeavor to make sure that your problem gets solved if there is a problem. And you're also free to just go and talk science with people. So go register for an account and use it to your heart's content. These slides are available on the website, so I wanted to put a bunch of links to resources for you in the slides, including the documentation for Data Preview 2 and Data Preview 1 and the science platform, as well as a link to actually go to the science platform itself, and various other resources for you. So this is just there as a reference for you. Okay, so on to the data that you are so eager to work with, I hope. There was a session earlier this week on the early science program. This is basically our way of saying, like, we don't want you to have to wait until data release 1 to access real on-sky data. So I won't go through this in detail because there was a whole session on it. Just to say that these data previews are our way of getting some early data out to you and available. And as you may have heard, early data preview 2, EDP2, was released on Monday of this week. So those data are available to you. And many other data products will be made available to you before the end of this year. So the early DP2 includes the deep COAD images and all of the varieties of catalogs that we will be producing. So the full DP2 coming later this year, we'll include all of the single visit images and the difference images. So for now, you'll just have access to the deep COAD images. This table is probably hard to read, but the main point here is that you can see the availability of different data products in different data releases. This is just to highlight that the only image data product in EDB2 is the deep COADs, but all of the catalogs are available. I put the line in the wrong spot, I just realized. Okay, so what is in Data Preview 2? The answer is lots of images that hopefully are as beautiful as this one. And they cover a roughly 3,000 square degrees area of sky in deep COADs. So that's the area where you see the little boxes. Those are what we call tracts that have deep COAD data. So wherever on this map that you see those boxes, like here, that's where COADs exist. So it's mostly in that swath along the ecliptic. And then there are a few deep drilling fields and special fields like these. And then the rest of the area where you see fewer visits, I should have mentioned, this is color-coded by the number of visits at each position. So this region with fewer visits, those single visit images will be available in the full DP2. And this just actually, I already said most of this, but it actually labels some of those deep drilling fields that I mentioned. There is a little bit of overlap with Data Preview 1, so if you want to do a direct comparison, that is possible. You can see in the far right that, for example, the extended Chandra Deep Field South has almost 300 visits overlapping. Okay, so the data themselves were processed with version 30 of the LSST science pipelines. You'll see that's the recommended version to use when you go to log into the science platform. Right. Sorry, I can't see my slides here, so I'm reminding myself from up there what I need to say. The deep COAD images are a little bit different than they were in DP1. They are still divided up into tracts and patches on the sky, just like DP1 was. And there is some overlap between the adjacent tracts and patches. We used some visit quality criteria to decide which visits contribute, basically based on the image quality, the full width half max of the PSF, and the transparency during that observation. One difference is this is for the first time using cell-based COADs. And basically this is illustrated in this image in the bottom right. If you take a bunch of visits at random or semi-random dither positions and rotation angles, and you go to COAD them, you're going to get a bunch of places where there are edges of images. And then you'll get, like this is showing the mask plane, where that's the edge mask. And that will cause discontinuities in your point spread function. So in order to remove those discontinuities from the point spread function, we do what's called cell-based COADs, where each 150 by 150 pixel cell only contains images that completely overlap that cell. And then you get something like this that doesn't have those edges cutting across it. For the most part, you won't notice the difference as a science user, but it's good to be aware of this. Okay, so this just shows you the COAD depth as a function of position. You can see that it reaches beyond 25th magnitude in some regions, especially in the deep drilling fields and some of the science validation fields where we made, many, many visits. But you can also see that it's rather inhomogeneous, because remember, this was data taken while we're commissioning the system. So it's not homogeneous over this whole footprint, but you can see that we're reaching at least 23.5 over almost the entire COAD footprint. This just shows you the average date of observation of each COAD. You can see again, it's kind of inhomogeneous. This is partly because parts of the sky are not, the same part of the sky isn't always visible. So you can see that the darkest colors are to the far right side. But you can also see when we were doing specific programs, you see sort of bursts in a very short date range. And just in one other illustration, this is the average full width half max of the PSF as a function of position. Again, you see it's very inhomogeneous, but is typically between the color scale runs from 0.9 to 1.4 arc seconds. So you can see it's generally just above 1 arc second average PSF. Okay, the next 2 or 3 slides have a ton of text on them, and we don't have time to go through it in detail because we want to get to actually showing you how to access the data products. But this is just a note, and these slides are there for you to refer to later. This is just to note all of the processing that was done, including, we of course correct for the instrument signature. We do lots of calibration. There's co-addition, there's difference image analysis, all of the detection, deblending, and measurement, including force photometry, and including linking together individual detections of moving objects. And you will see on our documentation website lots of description of how all of these steps are done. And again, we don't have time to go through all of this in detail, but this will help you get familiar with the terminology that we use for different catalogs. So static sky objects, catalogs of astrophysical things in the sky, are either going to be in a source catalog, which is the measurements from individual visits to a sky position, or they'll be in the object catalog, which is like, think of it as the astrophysical object in the deep COAD images. And then we do forced photometry at the positions of all of the objects. We go back to all the visit images and force a measurement at the position of each object. So that's the forced source table. And then we have very similar tables for the difference imaging analysis. So they have DIA source, DIA object appended in front of those. And so those are, again, just from the single visits versus the COADs. Right, and we do detect and measure and associate measurements of solar system objects as well. So the moving objects, they initially appear in the difference images. So they're in the DIA source catalog, but then you'll see there's a SS object, solar system object, and solar system source table. And we also make available the MPC orb, which is the Minor Planet Center catalog of known objects. And there are also catalogs of like metadata about observations, information about the conditions of each pointing, the central coordinate of each pointing, the time it was taken, which you'll need for light curves. So those are in either the visit or the CCD visit tables. And those are just tables cataloging all of the visits that are included. Okay, and this is way too much information, but just to note, each line is one of those sort of either a deep drilling field or one of those science validation fields. And this just shows you in the 6 bands, UGRIZY, across how many visits were taken in each of those fields. So you can see that there are some fields where for example, here, not quite tall enough, but that 225 minus 40, there are many hundreds of visits. So it's really great for time domain science. Okay, and the last thing I wanted to mention is what's new in DP2 relative to DP1. Obviously, we're covering a lot more sky area. This is great. It also includes regions at very low galactic latitudes. We actually cross the galactic plane. And we also have a large contiguous area. It's not a bunch of isolated fields, although you can see there are some isolated fields. We have some improved shape measurements, which these are from a code called Multiprofit. That is, there's a link to the tech note that describes it on the slide here. Those are provided in the object table. They're not only improved shape measurements of all of the objects, but they provide an improved method of star-galaxy separation. So this GRIZ model extendedness is a parameter that appears to do a better job of separating point sources from extended sources than what we had available previously. In addition, we have the shear object table for those of you who are interested in weak lensing. And we have the isolated star stellar motions table, which is a table of proper motions and parallaxes measured for a subset of the stars. And I already mentioned cell-based coads. All of the deep coad images are cell-based coads, so they don't have the PSF discontinuities that we previously had. And one last thing that, again, for most users, you probably won't notice a difference, but we did rewrite the image format. And one of the main outcomes of this, among many changes, is that the new image format plays much better with standard tools like AstroPy. So for example, the WCS plays with AstroPy's WCS tools better. Okay, so documentation of all of this can be found at dp2.lsst.io. And I think that's actually a link if you download the slides. So we have documentation about the processing, about the different data products that are available, as well as rendered HTML versions of all of our tutorial notebooks. So I think we have over 60 available already and many more coming. And so that's an excellent reference to keep in mind. So dp2.lsst.io. And then there is a journal article in preparation that I've also linked to on the slide here. I mentioned we have lots of tutorials. We'll show you how to access those in just a little bit. Basically, it's very simple. Within the notebook aspect of the science platform, there is a tutorials drop-down menu, and you just can click on whichever one you want to load, and it'll pop right up. We are working on portal and API tutorials. I think we don't have any up on the web page yet, but coming very soon. And finally, I just wanted to mention that we have these virtual seminars that we're holding next week. And these are to get you started with EDP2. So we have 2 different sessions at 2 different times on August 4th and also on August 6th. So do check those out if you're interested. We'd love to have you. So the place you access all of this is at the Rubin Science platform at data.lsst.cloud. And you'll see demonstrations of the portal and the notebook means of accessing the data products. And I guess we probably don't have time to do an API demo today, but we will have tutorials showing you how to do that as well. So now I think we'll, if anyone has any questions really quick, we can do that. And then we will have Gloria give us a demonstration of the portal. And then following that, Christina will demonstrate the notebook. So yeah, Louise.
Thanks. Very excited to use this data set. And I heard that it was easier to access PhotoZs now too. Is that true?
Good question. Yes, the PhotoZs are available. They're in the LSDB in the HATS format. So there is a demonstration of how to access those in the LSDB tutorial notebook.
Thanks, Jeff. So you explained that we have co-added and non-co-added images, and I know a little bit of the complicated history of how that was decided. So, but the if we want to look at the catalogs and we're interested in those two groups of things separately, if I only want to look at the co-added catalog or the non-co-added catalog, how do I do that? Is that possible?
Oh yeah, those are completely separate. So the catalog of measurements from the deep coads is the object table.
Okay.
And then the measurements from the single visits are in the source table. So they're in completely independent tables.
Okay. But if I just wanted that region, which was not, so you showed the picture, right? So there's the co-added stuff with the squares on it. So
right.
Just by going the object table, I get that. Now, what if I exclusively wanted the stuff which is the non-co-add? I mean, because the co-added stuff is also going to have single visits. It's going to have multiple single visits, right?
Yeah, it is.
So,
like something like this, yeah.
Yeah, or go back even one
more, yeah.
Right. So like if I want the stuff in the squares, I do the object table. What if I wanted the stuff that's just in the blue without the squares on it? Is that possible? I'm just curious.
That's a good question. The only way I could think you would do that is you would just use spatial queries. Yeah. Any further questions before we get to demos?
Just wanted to add, if you are looking for light curves, we recommend not to use the source table. We recommend using the forced source table or the forced source on DIA object table.
I'll add that in our tutorial notebooks, we try and provide guidance on things like that. Okay, so do you want to wear a lapel mic or?
Yeah, that would be better.
Do you have the mic?
I was like trying to figure out how.
I encourage you all to follow along if you'd like. Go to data.lsst.cloud and you can follow along with the demos.
Hello. Can you hear me? Yeah, okay. All right. Okay, so like Jeff said, if you have a RSP account, please go to data.lsst.cloud so you can follow along. So I'm going to be showing you the portal, which is one of the three aspects of the Rubin Science platform. If you were here for the Get Started with the RSP session, I do go more in depth than that session, so please bear with me. I will be using also some information from the DP2 documentation site. So if you want to do what I do, go to dp2.lsst.io, and there is a overview and observations. I'm just gonna use that for some coordinates. And also I have included, I put the link to the slides in the chat since I'm going to be doing some ADQL queries. So if you want to copy those, please open the slides. But okay. So does anyone need any time to sign in? No. Okay. All right. So I'm gonna click on the portal. And the first thing I'm gonna do is show you how to access the HIPS maps. I have a little tab over here since I've done it before, but if you don't have that little tab, you can go to the hamburger menu and there's a Rubin HIPS search. So I'm just gonna leave that in the, can you see it? Yep. Okay, so I'm gonna click Rubin HIPS search. And you'll see that there's several options for the data preview 2. I'm going to click on DP2 GRI pretty coad since it's a pretty map. And then I'm not going to put any coordinates. So I'm just gonna click search. Okay. So when you first land, it's pretty zoomed in. So I'm just gonna zoom out. Just to show you. Okay. So you'll recognize this from the slides that Jeff just shared, but you'll recognize this stripe, which is the White House deep area, and there's a bunch of smaller fields and also the deep drilling fields. So I'm going to zoom in into some of the deep drilling fields, and for that, I'm just going to mark them because I cannot tell just by looking at them in a sphere. But I'm going to go to the DP2 website, scroll down to deep drilling fields and grab the coordinates for Cosmos, which is 150.1 and 2.1. Easy to remember. So you'll see here, there's some tools. There's a little one that looks like a target. So I'm just gonna go click on that and put the position that I'm interested in, and that should put a little mark. So if you don't have access to the website, you'll see hopefully you can see the coordinates that I'm entering. So I'm gonna go mark that. So that has now put a little target on Cosmos. So you can zoom in. Now I want to see another one of the deep drilling fields. In this one, ECDFS, that's one of the ones that does overlap with the data preview 1. I'll have 2 little targets, and you'll see here there's a little layer, and that shows you all the things that are layered on top of the HIPS map. So I'm gonna just put the different deep drilling fields that I selected in different colors so I can tell them apart. But I'm just gonna change the color. So now I can go between these 2 fields, see what was covered for the data that's included in the DP2. And lastly, where is it? Yeah. So I believe there's data from first look as well. Somebody correct me if that's not true, but I'm going to put those coordinates there as well, just so we can see what it looks like. And you can see some beautiful galaxies here. But the point of this is just we have these beautiful maps that you can explore so that you can see, it's like what exactly is included. What does that look like in color. Does anyone have any questions about the HIPS maps? Or missed anything that I did?
So I noticed that if I wanted to read off the coordinates,
Mhm.
so notice on the bottom you have it in decimal
Yeah.
degrees, which would be great for me because I can't handle hour angles.
Yeah. So, if you
So
click-
how can I flip that?
if you click on it, if you click on the little EQ, I guess some people might not be able to see it.
Oh, in the lower left-hand corner, you can click on
Yeah,
that.
bottom
Oh, I
left-hand
see.
corner. And you can switch between, I just clicked on decimal.
Perfect. Thank you very
Yeah.
much.
Okay. Now, next up, I'm going to show you how to retrieve a deep coad. And for that, I'm going to do it two ways. I'm going to use this query that I've already included, and then I'm going to show you how to do it manually, just clicking around. But if you want to just like copy that from the slides, it's slide 33. And so in order to access the images, you have noticed that there's like all these different tabs on top. There's images, catalogs. You can also retrieve alerts, like single alerts. But I'm going to go to the images tab, which allows you to query for images with OBSTAP. Now, you can click around, which I'm going to show you how to do, but you can also just put in a DQL query. So I'm just going to take what I just copied from the slides and put it in here. Since it does take a second, so I'm just gonna search for that and then show you how to do it manually. Okay, so while that's running, I'm going to go back to the images tab. Oh, okay, that took no time then. But anyway, so you can do the ADQL or you can do the user interface. And for that, you have to go and select your observation type. So since we want to look for coads, that would be a calibration level 3, which also includes difference images. However, in this early DP2, there are no difference images. But you would select which kind of image you want, and then you can see what instruments exist, LSST ComCam or CAM, LSST CAM. And you can also select to only retrieve things from the DP2. And since calibration level 3 does include 2 kinds of images, you want to make sure to select a subtype, which would be deep coad. And then in that query that I had, I was using the coordinates for Cosmos. So 151, 2.1. So I'm going to look for deep coads that overlap the center of Cosmos. And I click search again, sorry. But I'm going to cancel that since I already have searched it. But anyway, so these are the deep coads that overlap the center of Cosmos. You see that there are 6. Hopefully you can read that. There is one for each one of the LSST bands. And so the portal results will show you your data product, which in this case is your image, some graph, and then a table of results. And if you click around in the table of results, you'll see that it changes the image. And you can also just like look at all of the images at once, clicking that little grid. So one thing, you can also see different image metadata. So if you click here, you'll see all of the different things, all of the image, the contents of the image that you get. So you get like your variance plane, different things like mass fractions. I think that's what it says. Yeah. So you have a lot of useful information that you can access from the portal. The masks. So that's how you access a deep coad. Next up, I'm going to show you how to grab catalog data that overlaps this area. But before that, are there any questions about the images? Okay. So I'm gonna go back to the slides. And I have a query already that I'm gonna tell you what it says. So for that, I'm going to go to the tab that says catalogs and go back to edit ADQL. And so for this query, I am selecting coordinates and different magnitudes from the object table. So, so the object table has a bunch of different flux measurements, but it does have magnitudes already calculated for some of the types of fluxes like PSF and C model. So for that, I'm just grabbing the coordinates and then C model magnitudes and PSF magnitudes in the G, R, and I. And I'm grabbing that from the object table, and I'm doing a spatial query around the center of the Cosmos field, and I'm constraining it to be I-band magnitudes between 18 and 25. And then I'm just going to click search. And while that is running, I'm going to show you how you might do that by just clicking around. So in the catalogs tab, you'll see a thing that says collection. So here's where all the different data releases will live. So right now it's default DP2. And then you can see all of the different tables that exist for the data preview 2, which were also included in Jeff's slides. So I'm going to query for things in the object table, which are things that were detected in the deep coads, and also force photometry at the location of sources. So if you wanted to just by hand do that, you would select object, and there are some columns already pre-selected, and you can see which ones are already pre-selected by clicking this little filter. And you can see all of the different magnitudes. If you wanted to specifically look for things that are around the center of Cosmos, you would put your spatial constraints here. And then I believe that ADQL query was 60 arcseconds. But you can also input some constraints. So in the query, I had a I-band PSF magnitude between 18 and 25. So you can put that here where it says constraints. And I'm forgetting my math. So it's less than 25. Greater than 18. Okay. Hopefully that was correct. But yeah, you can click search if you're doing it that way, or it should already be in the results if you put in the ADQL query. So here, this is, you also, in the results, you also get access to the HIPS map as by default under coverage. But the actual image would be here. So since I already looked for the image and I look for catalog data that corresponds to one of those images, you'll see here that it appears nicely on top of the image, right? So you could zoom in here and see which points were actually detected and considered an object, right? So I'm going to pause here for a sec before I move on to the next thing, which is I'm going to try to make a color magnitude diagram. Okay. So you might have noticed there is a graph here. Currently not the most useful graph. It's just plotting by default the coordinates. But you can change that to whatever is included in your search. So if you click here on the little gear, it gives you the option to change your X and Y axis. So for the X axis, I'm going to do some math. I'm going to say G PSF magnitude minus R PSF magnitude. And then in the y axis, I'm going to select the R PSF magnitude. And then that should change here. And now you have a little color magnitude diagram. Correct. But you can also enter some constraints after the fact. So if you wanted to narrow it down to like things that were less than 23 magnitude, you could do that, and it will also update your graph. Yeah. Any questions about how to edit your graphs? Okay. And lastly, I wanted to just show you how to plot a light curve. So unfortunately, the portal in the interactive way, you can't join tables. And in order to make a light curve, you have to do a table join between your force photometry tables and your visit tables. So I'm going to go back to catalogs, and I'm going to do edit ADQL. And I'm going to tell you a little bit about what's in the query. So the use case here is you have the coordinates of an object that you might already know is variables, and you want to get its light curve from the force photometry. So one thing you should not be doing spatial. I don't know if you even can anymore. On force photometry tables, you have to match to something like the object table or the DIA object table. So for here, you'll notice the spatial query here is actually with the DIA object table, which has light curve statistics. And then from that, I'm joining with the force source table based on the DIA object ID. And I'm also joining the visit table on the same visit that exists in the force source on DIA. But yeah. And then we're also only looking for things that are in the R band. Did anyone's query finish? I saw Jeff, you were copying something. You didn't try it? Okay. Mm-hmm.
Thank you. So is there any plan to allow triple joins also with the graphical interface?
Sorry, what?
In the portal aspect, is there any plan in future to implement the possibility to join 3 tables and so do the light curve without using the ADQL?
You have to use ADQL to join any tables. Oh, yeah.
I mean, just for light curve queries, there's a built-in way to do light curve queries from the UI.
Oh, okay.
So if you go to back to the object result tab, and then at the top is next to coverage, there's a data product tab.
Oh, okay.
That's a light curve.
Yeah.
For
Okay.
that object.
Yeah. Sorry about that.
So So that's already there. And that works for the object table and the dia object table. You can search for both force source and dia source and force source on dia object type light curves that way. And then for building joins, if you go to the catalog search, if you want to just clear the ADQL query just for a moment, just for clarity, I hope you have it saved somewhere. If you open up the DP2 schema browser on the left, just that plus sign by DP2.
Oh, sorry. I thought you said, yeah, that's schema. Yes.
Yeah, and then just open up object just as an example at the top. There's a joins available at the top of that list. You open up that folder and that gives you the keys for what you can join to. And if you click on that, it will insert the necessary ADQL for the join into the box. So it knows which keys join tables. So we do have on a list to have some more general way to kind of somewhat more automatically build up joins. That's not quite there yet, but this is what we already have. So we have sort of canned joins for things that like light curves that people will frequently ask for. We're shortly going to extend that to the solar system tables. It didn't quite get done in time for the release, but we can do that very quickly. It's easy to configure for that. So that's at least a partial answer to your question.
No worries. No, I remember that being a thing, and then for some reason when I looked earlier today, I did not click on data product and did not see it, and I was like, no, I gotta show. But thank you. But I'm gonna run it again just so I can finish my little showing you how to do it manually. Oh yeah, yeah. So okay. So that's my query. But yeah, you'll see here in the job monitor, you can see not just from the portal, but like from the notebook as well, all of the things that you've completed, and also things that are currently running. So I sometimes have queries that I don't want anymore, but are still ongoing. So you could stop it here. Was there something specific that you wanted to?
You can see what your query was by clicking on the little eye in the circle, and then you can reload the results of the query by clicking on the green icon next to the eye that looks just like the icon on the results tab. So, you know, that kind of is the visual link that tells you that. So if you want to reload a query result, that will do it.
Okay. All right. So that little query did finish. And great. So if you were to just try to do the light curve yourself, you can once again go to the little gear. And here you would select your date, which came from the visit table, and then your PSF difference flux. So these particular coordinates were from extragalactic transient, and I believe they were in Cosmos. And so if you want to, like, you could like zoom in, you see here that it's it had a time where it was like rising. So you could just zoom in there. And yeah, so you could just look at the light curve. But that's all I had for the portal. Did anyone have any more questions? Okay, then. Oh.
Fun for people to know about. It looks like you don't have an image left from but maybe if you go back to the OBSCore table, yeah, we can bring up an image from there. So Gloria showed you how you can see the mask, which is a large set of Boolean flags for every pixel that are generated by the pipelines. It's possible to overlay the mask on the image. So if you go back to the image, Gloria, and then you go to the layers dialog, the thing with a little 4 on it. It says enable mask layer. And now there's a list of all the masks that are that are in there with descriptions of them, and you can turn on one that you want. So like saturated might be interesting in the context of this particular image because it looks like there's some. You can just close it.
Yeah.
Yeah, there we go. So that green stuff is a mask overlay. And then if you go back, if you reopen the mask dialog and you kind of slide it out of the way of the image, you can just, that dialog is movable. And you hover over like one of those green points, you'll see that it tells you which masks are actually enabled by turning on color on the names of the masks. So that's a much easier way to navigate the mask data than just trying to look directly at the mask layer itself.
All right. Good. Let's stop sharing, and then I guess Christina will do the notebook. Oh, yep.
No, yeah. So this might be a question that's like more broadly about DP2 and not necessarily related to the portal. Is there a way to access versions of the deep coads that haven't had background subtraction applied?
So you can't, it is impossible to co-add images that have not had any background modeling done because you need there's a lot of normalization you need to do to the images before you co-add them, and normalizing them to a constant background, a constant 0 point, a constant astrometric projection is a necessary step. There are two backgrounds that are available in DP2. One is the per detector background that was applied to each of the detector visits before co-addition into the deep coad. There was also a per visit background model that was applied to the visits and detectors that went into the so-called pretty coad. So the HIPS map that Gloria was showing, the RGB one, the GRI one, is the pretty coed. The difference between those two backgrounds is attached to the deep coed. So when you read a deep coed in from the Butler, you can there's a method which is, I think, apply background pretty. We'll show it in the pipelines session tomorrow, and I think Jeff definitely has it in one of the tutorials on how to do that. So you can turn your deep coads into pretty coads using that method, and this is a new feature as of DP2 and hasn't fully been validated. It looks nice. The full focal plane backgrounds, they look nice in some areas. They didn't look so great in some other areas. They weren't robust enough to use for the coads that we were going to do object measurement on, which is why we ended up making a second round of coads later. But definitely take a look at them.
I think we have time for more questions for Gloria if there are any. Otherwise, I can get started. Okay, great. Okay, the person asking a question on Zoom can unmute and ask the question.
Okay. So instead of deep image, I checked there are like 100 images available in that particular field I'm interested in. But then I checked the individual one. There are like, image 10 to 20 has a problem. So I want to remove that one. Can you basically do a number of image range? Then I can do mosaic using this platform. Like I want to only do 1 to 20 image to mosaic. Is it that kind of option available? Instead of having a 1D image.
So if I understood, you did a similar thing that I did of looking for coads in a particular region, and you have a bunch of like 20 of them. Is that what you said?
Right. I mean, there are like like 100 on the image available. I want just give the range of numbers. Only I want to mosaic those images. I can give the frame number and make this platform make a new image.
Yeah, so for the query that I did, there was only 6 of them, for one for each of the filters. But when I have more than that, it's because there are several like tracks that overlap that particular spot. So you could just pick like a particular one that like's the best that for the particular point that you're looking for. So I don't know if you notice in the images that I showed, the actual center coordinates were kind of a bit to the bottom right. So if you have like a bunch of different tracks that overlap your the specific point that you're interested, there might be some that might be more centered or something like that. But if somebody else has something to add, I hope I understand. I hope that answered your question. If not, somebody else could share some insight.
That's enough answers. Thank you.
All right. We also have time at the end for questions if someone thinks of something. In the meantime, I will go through an orientation of the notebook aspect of our Rubin Science platform, and also demonstrate how to access some of the DP2 data products from the notebook aspect. So if you've been following along on your RSP account, you can just go back to data.lssd.cloud and click on the big notebook button in the middle of the landing page. And that will bring you to what you see on my screen here, which is it's showing a terminal with the notebook aspect. And from this platform, you can go to the tutorials menu. There's a range of tutorials we prepared for all of the different early release science data sets. So we're today going to go to DP2. And then you can see all of the DP2 notebooks that are available to help you get started accessing the DP2 data. So today I'm going to try to fit 3 notebooks into this 30-minute time slot. I'm going to first show a notebook that shows how to access DP2 images. So these are deep COAD images that are available. Then I'm going to show how to access some of the catalog information using the RSP tools through the notebook aspect. And then at the end, I'll show an overview of the DP2 data sets that are available and how to access those. All right, so if you're following along, you can go to the tutorials menu, go to DP2, and the first thing we're going to do is go to the 100 series about how to use the RSP tools, and then we're going to go to 103 image access and display, and I'm going to open 103.4, which is image display with Firefly. So that's going to pop open this notebook here. So Firefly is the visualization and interaction tool for viewing and navigating images with the RSP. And you saw this in the portal, but you can also access this from the notebook aspect. So I'm just going to show you in this notebook how to access DP2 COAD images and sort of do some basic navigation and other things to better understand the images. All right, so all of our notebooks have a bunch of narrative text to help you sort of get oriented and understand what's happening. In this notebook, we're going to access a bunch of LSST pipeline tools by importing them. And so I'll try to explain some of what those are in case you've never seen the packages before. So the first thing we're going to do is import some packages here. Some important things that we're going to import is the Butler. So the Butler is the Rubin Science Platform's interface for accessing, reading, writing, and managing data sets in the RSP. We're going to also open AFW display. So AFW stands for Astronomical Framework, and this is sort of the display functionality that allows you to display images. There's some other things in here. One of the other things we're going to do is open Firefly, which is here. So we're going to run this cell to import these notebooks. The first thing we have to do is instantiate the Butler. So the Butler, I said, was the method by which you access and read and write data in the Rubin Science Platform. We have to point the Butler to the right data set. So there's two things you have to specify. The first is the repository. So we're going to point that to the DP2 repository. So you can see here how to do that. And then we have to point it to the DP2 collection over here. Okay, so we're going to run that. And then we can call the Butler later to have it serve us DP2 images. All right, so we're going to also set the default backend of the AFW display functionality to be Firefly. So that's the interactive visualization tool. You can also replace this if you prefer to not work with the interactive tool, you can also replace this with something like Matplotlib and plot images more in the notebook interface. And so we have some other notebooks that demonstrate how to do that. So what I'm going to do here is first set the backend to Firefly, and then I'm going to ask Firefly to load a display for us. Okay, so that's going to pop up this Firefly display, and I think it's kind of nice to have Firefly be offset from the notebook so you can look at both of them at the same time. So what you can do to do that is just click on the tab and drag it over, and you'll see this blue box will move around, showing you where Firefly is going to go to. And here you can have both the Firefly visualization and the notebook in the same window. And I lost my place. Hold on. All right. Yep. So the instructions in the notebook show you how to do that next time if you want. Okay, so the first thing we're going to do is query for an image to display. So you have to, in order to find an image and specify an image, you have to identify the location on the sky. And another unique identifying criteria that you need is to specify the band for a deep co-ed image. So here I'm going to specify these coordinates. This is in the extended Chandra Deep Field South. This is a famous extragalactic field. And then I'm going to specify the R band. So I'm going to store these here. And then we're going to, this is a little bit, I'm just going to close this to just let us maximize the code here. All right, great. Okay. So now we're going to query for a deep co-ed image that overlaps this point on the sky in the R band that we had specified. So similarly to what Gloria showed you, by using the ADQL query language, you can send queries also through the notebook aspect. So here we're going to specify that we want the band to be R band. So we stored that as band here. And then we want to identify the patch. So the deep co-ed images, like Gloria and Jeff had mentioned, are broken up into a grid of patches and tracts. And so you have to find the specific patch that overlaps this RA index in order to retrieve one deep co-ed image of that area of the sky. So we're going to specify that we want the patch to overlap this RA index that we specified. And then we're going to run this query to the Butler and ask the Butler to send us a deep co-ed image, or at least the reference for the deep co-ed image that is overlapping this point on the sky and also is of the R band. So we're going to run that, and it's going to store this image here in this deep co-ed. I see a question that just came up on the chat. Oh, sorry, I'll just keep going. All right, so now we have this, the Butler has sent us this deep co-ed image that we're storing here as deep co-ed. So now we're going to display that image in the AFW display, which will send it to Firefly. So we're going to hit that. And now the image is going to pop up on the right over here. in the Firefly viewer. So what you'll notice here is there's the science image in the background. We also have a mask of that flags pixels by various criteria so that you can sort of assess quality and also just know the processing history of various pixels. So those are all overplotted on top of this image right now with these colors, like you saw in one of the previous demonstrations. And so I'm going to show you now how to manipulate that mask. So first of all, right now everything is plotted, but you can set the mask transparency to 100, which will only show then the image without the mask, the bit mask on top. So here you can see the deep coat image here on the right. So you can also change this so that it shows the mask at a slightly different transparency. So you can see the background image and also the pixels, the pixel flags. And you can do things like print the list of masks that are plotted and the colors that they're plotted in. And so this kind of helps you to navigate what information is available inside this deep co-ed image. So you can also go directly into the Firefly viewer and access these things without calling it in the notebook. So for example, you can go to this little layers button over there and click that, and this will pop up the various mask layers. So you can do things like click on and off, you know, the detected pixels, for example, you can turn that off and things like that, or you can hide all or show all, things like this. Okay. So you can also do this from the notebook commands also. So for example, you can reset the mask transparency, but then ask it to plot only the detected pixels at a transparency of 80%. So there's lots of ways you can sort of manipulate what's going on here. You can also change the mask colors through these commands here. I'm just going to sort of quickly skip through this stuff so that I have more time to show you things you might be interested in doing, and just point you to these resources so you can later sort of investigate this on your own. So sometimes it's useful to set the scale. Wait, let me just return this to 100% here. Oh, actually, it's not 100% there. Okay, sorry. All right, so there are things you can do like set the scale of the background image. So you can ask the scale to be A sin H and Z scale, which are sometimes better for visualization. You can also directly in the Firefly viewer here, just change the stretch manually. So you can change it to linear or something else like that. So you can also zoom in and out either through the notebook or over here also in the visualization tool itself. All right, so one thing that I think people are interested to do is plot detected objects and other objects that you can query from the object table directly onto the images. So I'm going to show quickly how to do that. So I mentioned earlier that you have to specify a specific set of criteria to uniquely identify images. So one of those things is the filter, and the other thing is the patch and tracked on the sky for deep co-ed images. So we call this the data ID. So we've already retrieved an image, so we can just grab the data ID directly using this function here called data ID, and that returns to us in this data ID the unique identifier of that image. So now we're going to query the butler and ask for all of the objects in the object table that have been detected from this patch and tracked image. So here we're going to do that, and we're going to ask for just some basic columns from the object table here, including the object ID. Each object has a unique identifier, the RA and dec of that object, its extendedness parameter, which helps to determine whether it's a star or a galaxy, and then also there's a flux measurement here. So we're going to ask the butler to retrieve the object table for this specific tract that this deep co-ed image sits in, and then we have to give it the sky map, which Jeff had mentioned earlier, as defines the patch and track grid on the sky. So we're going to run that, and this is going to return objects to us. So these are things that met that criteria and are sitting in our patch and tract. And so now we're going to find the things from that tract that sit inside this specific patch. So every patch sits inside of a tract, and so each deep co-ed image is one subset of a tract. So we're going to ask for this specific patch that we're plotting here on the right. So there are 9,000 roughly objects that are in this patch of the sky. So I'll just zoom out a little bit more, just so we get a better view. And now you can take the RA index of all of those objects that we queried from the object table and plot them on top of the map. So here I'm going to run this screen, or sorry, this cell here, which is going to plot a dot where at each of so each RA index location of a galaxy, we're going to convert those to pixel coordinates and then plot those on here. So that's what I'm doing in this cell. And it's going to take a minute because there's 9,000 of them. And then now you can see on the right, these orange circles are sitting on top of every object that was detected in the object table from that query. Okay, does anyone have any questions on accessing the images or Firefly or accessing the object table from this particular image patch?
I noticed one of the commands before you had something I'd never seen before, which was it said bind equals bind.
Oh,
can you tell me what that was about?
Yeah, so where is it? Here. Okay, so bind, we defined bind to be this dictionary here where we were asking for a specific band and RA and DEC. And then bind is something you can feed to the query data sets method of the butler. And so does someone who knows more about this want to add anything? There's a number of ways you can do this. In this notebook, we chose to do it this way, but that you can also just feed it a query that meets the. So there's, yeah, I think in all of our notebooks, you'll sort of see that there's a variety of way to do some of these things. And so we try to demonstrate those. And in this case, this is one of them.
Regarding bind, we use bind. Sorry, this is Tim Janess. I wrote some of the butler. Yes, you can just F-string the thing straight into your query string, but the advantage of bind is that A, it works with things like lists and tuples automatically, and B, you don't have to worry about quoting. So if it's a string, it gets quoted automatically, and if it's a number, it gets handled. So it simplifies. You don't have to think when you're making the query string.
Okay, thanks, Tim. That's great. All right, any other questions? We can also take questions on this afterwards. Maybe I can just move on to if there's no other questions now, I'll just move on to the object table query. Oh, wait, is there another question?
Tim, sorry, this is Yusra. Do you need the where and the bind, or either or?
Well, the where is the query string, and the bind is how your parameters are put into the query. So the colon band matches the key band in the bind dict. And it gets
I see.
Yeah,
Sorry.
and it gets auto quoted for you. Otherwise, you have to remember how quoting works in where clauses and all sorts of things.
Got it. Thank you.
All right. All right, so if you want to follow along on the second notebook, we're going to go back to the tutorials menu, go to DP2, and then this time we're going to go to the 200 series called data products, and we're going to go to 201 catalogs. So here, depending on your science interest, you're going to see we have a range of different notebook subjects here that will help you access these different tables. But this time I'm just going to show the object table, which is what corresponds to the detections in the deep COAD imaging that's currently available in DP2. So I'm going to click on this and it's going to open up a new notebook, and then I'm going to close this Firefly viewer because we're not going to use that. All right, so so this notebook is going to demonstrate how to access objects that have been detected in the deep COAD images and are stored in the object table. So again, we're going to have the butler that we're going to load up, and now we're going to use also this lsst.rsp package, and specifically this RSP discovery package. So if you've been working with DP1 data, you'll remember that there are packages for accessing the table access protocol. So that's what we're going to demonstrate here. The table access protocol is now in this new package called RSP Discovery. So it basically works the same way, but it's in a different name. So the object table is a very big table with many properties in it. There's about 1,200 different measurements for each object in there, and there's something like 786 million objects that are detected in the DP2 data set. So that's a big data set. I'm going to import these packages, and I'm just going to define some parameters and functions that will be useful. So the first thing we're going to do is we're going to use the RSP discovery package, and we're going to point it to the DP2 data set here. And then we're going to get that TAP client, which will give us access to the table access protocol client, and we're going to call that service. So periodically, we're going to send queries to this TAP service and retrieve rows and columns from this table, this object table. All right, so I'm going to start the service. And then like before, we're going to open up a Butler, instantiate a Butler, and then we're going to point it to the DP2 data set here. So I'm going to run that too. All right, so since there's so many columns, it's really useful to know about the schema. So the schema defines all of these different columns. It's searchable, and there's a very brief description of what the column holds. So this link in this notebook will take you there so that you can sort of browse what's available. So here we're just going to use the TAP schema catalog to, or sorry, the columns of the TAP schema, and we're going to print it here so that we can see what is contained in the DP2 object table. So we're going to run this query to the TAP service, and it's going to take a few seconds. Or more seconds. And it's going to give us an error. Well, that was unexpected. Did I miss a cell? I'll try again. Are you all running this query at the same time? So any idea what I should do here? I ran this earlier and it did work, so okay, well, does anyone have any questions so far about this, just the beginning of this notebook? Yeah.
So if you go up to where you were setting the portal, yeah. So is the RSP discovery line, is that the equivalent of setting the sorry. Is that the equivalent of when you instantiate the Butler of setting which repo that you're using?
So when you have to point this to a particular data set, because we're going to query the tables contained in the DP2 catalog. So you do have to point this RSP discovery to a specific data set.
Right. But the reason I'm confused is I actually ran across this just the other day. But if you go down to your query, you'll find out that you're actually asking for DP2 dot something.
Oh, okay.
So why do you need to do that? Is it that you're actually asking for that particular repo, and that's where it, like if you go to your query, you'll say from, DP2.object.
I see.
So if you're all looking at the same place, then why is that necessary?
Yeah, that's a good question. Does anyone know why you specify DP2 twice? Oh, Gregory knows the answer.
So Gregory just said that DP2.object is just the name of the table. And is DP2 in that discovery thing? Is that pointing it at a particular repo, or is that, what is that thing?
There are two different questions being answered. The first question is essentially saying, on what tap service can I find DP2? It doesn't mean, doesn't imply that that's the only thing that's on that service. It happens to be the same tap service on which DP1 is available, right? So you can still ask for DP1, right, as it happens, because they happen to be on the same tap service.
So that's
Right.
the name of the
The-
tap services,
Yeah,
and there's more than one of them.
yeah. I mean, they're basically right now for science users, there's just the one tap service. When the prompt products database is live, that'll have its own tap service. So when you ask,
Okay, I guess I was tricked because
Yeah.
it was DP1 before last week, so.
yeah.
Okay.
So
Okay.
so we don't want to like train you to assume that different releases will be on the same tap service. They happen to be, and all that first line is doing is saying, where is the tap service on which I can find DP2?
Got it. Thank you very
Right.
much.
And then, but the name of the data on that service still has the DP2 prefix.
So to clarify, you're saying that I could replace this DP2 with DP1, and
It
it's
would
still
happen to work at
it-
this
okay,
time
okay.
because they are on the same database and the same tap service.
Okay.
Yes.
Okay, I mean, I can also move on. This sort of shows you how to access DP2 object table, but I could just go on to the overview notebook, which is already loaded. Okay, yeah, should I just go through I can do that one. Sorry.
I mean, you can just ignore that error, run the rest of the code.
Okay. All right. Thanks, Frosty. All right, great. Okay. So we just ran the query successfully. And now we're gonna dump it to a table called results. And so yeah. Okay, so we can store the results of this query as an AstroPy table. So that's what is stored in results here, and printing it truncates because it's a lot of different columns, but you can kind of see here the different columns that are contained in the query, and then also a brief description of what the columns are. Okay, so there are some options here to sort of look a little closer in there. Sometimes it's nice to just delete things that you store to free up memory. So there's some key columns that are probably of interest to people. There's the object ID. Each object has a unique object ID identifier. There are RA and DEC coordinates of the centroid, as well as uncertainties on that. And then there are something like 26 flux measurements. We have some notebooks that help you navigate those flux measurements. We're just going to highlight a couple of key ones that might be broadly applicable. So PSF flux is good for unresolved sources, and C model and Sersic flux are good for resolved sources. They assume a shape, and then it integrates that shape out to infinity, so you end up with a total flux that you can use for luminosities or stellar masses or things like that. I'm just going to skip through some of these. We have a number of shape measurements. If you want to come to the galaxies session tomorrow, you can hear more about all of the shape and the photometry as it relates to galaxies. We'll talk about that there. Okay, let me see. These are, so yeah, so here you can just, this shows some of the descriptions again. Some key advisories about these query searches of, it's good to avoid the full table search. The tables are sharded by RA and DEC, so you can, we advise that people do spatial constraints on their queries just to keep the results manageable, and to keep the queries manageable. So I'm going to show you a demo of how to do that right now. So again, this is the ADQL query language. So you can select, and also Gloria showed this in the portal. This is basically the same language. You can select a number of columns including these RA and DEC and also some of the magnitudes that were measured from the photometry. The DP2 object tables where we're querying it from, and then we want to do the spatial query on the sky. And so you can set this where command to say that we want the query to return objects with RA and DEC that meet these criteria. So it's basically within a circle of 0.2 degrees on the sky radius at these center coordinates. So you can set up that query and then send it to the TAP service, and it's going to run for a few seconds. And then we're going to store that in a table again. There are 40,000 objects with the query in that part of the sky that we requested. You can also plot or print the table output. So here you can see all of the flux measurements and the RA and DEC of the sources, and it's truncated because it's very long. But then you can sort of access these table columns and do science with those things. And I am totally out of time. So I'm going to stop there. But please feel free to look through our DP2 tutorials that will help you sort of see some of the other functionalities that we didn't have time to cover. So are there any questions about that or any of the talks today? Or we could just go to the coffee break too. That's fine.
Like Christina just noted at the end there, we do have lots of tutorials that you can go through on your own time, because of course we can only cover so much in these sessions. But if you go and poke around at any of those, track any of us down if you have any questions. Otherwise, thanks for being here.